Hi, and welcome to the School of Maths and Stats. My name's Thomas Britz, and I'd like to go through this problem 67 in the course MATH3411. The problem here is about finite fields and minimal polynomials and things like that. So let's have a look at the top line here. Let GF of 16 be something, something, something. Okay, so what's all this about? Well, it's about finite fields. In particular, it's the finite field of size 16. There's only one of them, but we can express it in different ways, and that's what the next parts say. So this is going to be what you get if you take some element, some primitive element alpha. So this sort of indirectly says that that element is going to be primitive. And then you raise it to all sorts of powers and multiply it by the binary numbers 0 and 1. So you could view it as the as what you get if you look at all the ratios or rational forms of alpha and the binary numbers. That's a little bit cryptic. The main thing here is just that this implicitly says that we're dealing with a primitive element which we're calling alpha. The next part here is slightly less cryptic. It says that, well, if you take the binary polynomials with variable x and then you mod them out by dividing by this polynomial here, x to the power 4 plus x plus 1, and look at the remainders, well, then you get exactly this field here. So there are two components here to describing this field, expressed in this particular way. There's the additive way of understanding it. So if you look at all these binary polynomials and you're dividing out by this polynomial here, this degree 4 polynomial, then you'll get all the binary polynomials of degree 3 or less. So in other words, all the binary polynomials of degree 0, or all the constant polynomials 0, 1, or the binary polynomials of degree 1, 2, and 3. So the degree 3 polynomials, or rather these polynomials here, you can express them in terms of 4 coefficients, each of which can be zeros and ones. So you have 16 binary polynomials, and you can view those as the elements of the field there. And you can add them and subtract them, and that's how these numbers of the field work, just like a vector space or a little bunch of numbers that you're polynomials that you're adding together. On the other hand, the multiplicative structure is a little bit different. For that, we need this primitive element there. So this alpha there, well, that's really just another way of writing x, in this case here, where we're saying, okay, alpha is a root of this particular polynomial here, and it turns out that this polynomial is irreducible. We have shown that previously in another problem, and we've got that m of alpha is going to be equal to 0. That's we're deciding. This is how it is. And what do we mean by that? Well, we mean that if we plug alpha into here, so we have alpha to the power 4 plus alpha plus 1, then what we're really saying, but we're just writing it up with alpha and thinking a little bit differently about it, is that we've got the polynomial x to the power 4 plus x plus 1, and that's congruent to, well, 0 if we are modding all of these polynomials by that polynomial there. So we're modding itself by itself. So mod x to the power 4, if I can squeeze this in here. So yeah, m of alpha is equal to 0 in this general setup here, the way that we calculate it here. So another way of saying that is that alpha to the power 4 plus alpha plus 1 is equal to 0 if we get rid of congruences and mod terminology and just say, well, in this field here, g of f of 16, the way that we've defined it, at least here, in terms of this particular primitive root of that particular irreducible polynomial, then we've got that this is true. And what does that mean? Well, or rather, what does it imply? It means that, well, alpha to the power 4 is equal to minus alpha plus 1. Minus 1. And plus and minus 1 are the signs of things are irrelevant here because we're talking about binary coefficients. So minus 1 times alpha is the same as plus 1 times alpha. So we might as well just write alpha plus 1 there. Because, yeah, we're dealing with the binary numbers as coefficients. And there we go. why did I just talk about that? What's that got to do with anything? Well, remember I was talking about first the additive properties of this field, and also then the multiplicative properties of this field, and those are the ones that I'm explaining something about right here. And how does this tie in with that? Well, have a look. And I've actually drawn up the times table there, so to speak. I'll talk about that just in a second. But this here is how I got the times table. So I found out that alpha to the power of 4 is equal to alpha plus 1. So when I was writing up this table here, and again I'll say what that table is, I said alpha to the power of 1 is alpha, alpha to the power of 2 is just alpha squared, alpha cubed is alpha cubed. So far that's not particularly informative nor interesting, but when we get to alpha to the power of 4, then we can use this little recursive identity here to say, oh, okay, I can simplify it down to alpha plus 1. And what I'm really doing here is just using this modular arithmetic. So mod that polynomial there. And alpha to the power of 5, well, that's just what we've got if we take the previous expression, alpha to the power of 4, and multiply by alpha. So we have alpha squared plus alpha, and then alpha to the power of 6 is equal to alpha to the power of 3 plus alpha squared. And alpha to the power of 7, well, here again, we get that that's equal to alpha to the power of 4 plus alpha to the power of 3. So that collapses because alpha to the power of 4 is equal to alpha plus 1. So alpha plus 1 plus alpha cubed. And if you rearrange those terms there, then you get exactly this expression that you can see up there. Hopefully you can see it properly. Alpha to the power of 7 is equal to, well, alpha to the power of 3 plus alpha plus 1. And then you can continue in the same way until you filled out the whole table, until you get to 1, which you do in alpha to the power of 15. So I said that this had something to do with the multiplicative properties of this field. And what I really meant there was that I want to create a times table for all the elements in the field here. And we can express those elements as those binary polynomials. And you'll see over here, if you have a careful look, all of the non-zero binary polynomials of degree up to 4 are in fact listed here in some order. And I could take all of those 15 elements of the field. So we could have a little times table here with all of the 15 polynomials there and the 15 polynomials here, and then just list them up and say, oh, okay, this polynomial times this polynomial is equal to some other polynomial, mod this, and we could calculate that, but it would be a big times table. So here's where this table comes in and improves things dramatically for us. So we've got a primitive element, so we were able to do all of this stuff here, which gave us this table here. And this table here is actually a times table indirectly, and that's how we're going to that's what we're going to look at right now, in fact, in part A of this question. So I'll show you how this table works. It's a very compact and neat form of timetable here. Instead of some big timetable, we just have those 15 entries, and what can we then do with them? Well, in the first part of the question here, we have to look at alpha to the power of 3 plus alpha plus 1 and find its inverse. What? What do you mean? So 1 divided by that polynomial there. What sort of thing is that? Well, this is an element of the field, some polynomial, and what sort of polynomial do we get if we take 1 and divide this polynomial by it? That seems crazy if you're not used to finite fields. But here we've got a table. So we've got alpha cubed plus alpha plus 1. We can look at the table and say, where is it? Alpha cubed plus, here it is. Cool. So this is alpha cubed plus alpha plus 1. That's actually just the same as alpha to the power of 7. So this is talking about alpha to the power of 7 inverse. Okay, cool. Now that's the same as alpha to the power of minus 7. And so what? Okay, we can do better than that. We can say something a bit more specific than that, because let's say that we say alpha to the power of minus 7 times 1. We can do that, that's fine. And that's the same as alpha to the power of 7 times alpha to the power of 15. Why? Well, because alpha to the power of 15 is exactly equal to 1. So we can express 1 as alpha to the power of 15. And that gives us all of this is equal to alpha to the power of 8. Yay! And there we have our solution, well, you could also express it in terms of one of these polynomials that has degree less than 4, in which case we could use our table again and see where's alpha to the power of 8. Well, that's here. And that gives us another way of expressing the solution, which is alpha squared plus 1. And we are done. So you see, here we could use the table to do division. And yeah, it was quite simple. We just use it backwards and forwards, or in this case, well, actually this was backwards and forwards. So there we go. So we can use this table to do division and multiplication, and that's in fact what we're going to do in the next part here in B. We've got this polynomial, which you recognize from above. It's the same polynomial, alpha to the power of 7. So we might as well write that, times alpha plus 1. And we could just write alpha plus 1 and divide it by the next thing there. Or we could look at the table to make things easier for ourselves. So let's have a look. Alpha plus 1. Where is that in the table? There it is. Oh, that was our alpha to the power of 4. So maybe I should have even just remembered that. And we're dividing by another polynomial here, another element of the field if you want. Alpha cubed plus 1. And what is that in the table here? There it is, alpha to the power of 14. And if we tidy that up, that's equal to alpha to the power of 7 plus 4 minus 14 is minus 3. So 11 minus 14 is minus 3. And that's okay, but it might be nicer to write it as alpha to the power of 3 minus 3 plus 15 again, by multiplying by 1, just like we did above. So that's alpha to the power of 12. Yay! Or we could also write it up as this expression here. Maybe I should write it here. Alpha to the power of 3 plus alpha squared plus alpha plus 1. And we are done with the second part. And again, you see that, well, if we were trying to solve this without knowing anything about finite fields, you might say, "What? That's scary. These are really polynomials, and we're saying this polynomial times this polynomial somehow divided by this polynomial give us whatever." That would seem like a lot of work. But because we've done all the groundwork, or well, technically speaking, we've done half of it, and I did the rest before making this video. But once I've got this little table here, then all of these things that we can do here turn out to be really simple, and the stuff that we'll be looking at in parts C and another part D, we'll be using this table a lot as well, just to simplify and make things easier for ourselves. So, speaking of which, part C. Find the minimal polynomial of this. Oh, I recognize you. That's alpha to the power of 7. Find the minimal polynomial of alpha to the power of 7. So, let's write that as m7 of x. Now, first of all, what is that polynomial? Well, it's a polynomial that has this as a root. Okay. How do we construct such a thing? And also, how can we make sure that it's the smallest possible polynomial? Well, let's have a look at that. So first of all, the type of polynomial that we're after is going to be a binary polynomial. So it's going to have the same coefficients as the base number system that we're looking at for the coefficients of all of these elements of the field here. So it's going to be a binary polynomial, because otherwise we could just say, and this is sort of a common point of misconception or possibly confusion, that, well, if we want the smallest possible polynomial with alpha 7 to be a root, why don't we just take x minus alpha to the power of 7? That's definitely small as possible, but that's not allowed, because we've got a coefficient there that's binary, yeah, sure, 1 times x, but here, whatever that is, that's not either a 0 or 1. That's a whole polynomial by itself. In fact, it's this polynomial that we have there. So this is not the sort of thing that we're after. We're after just an expression in terms of powers of x that are multiplied by the zeros and ones in this problem here, or more generally in terms of the coefficients that we might have here. If we're different fields, it might be some different coefficients, zp in general, where p is prime. So that's not good enough. We have to do more. So, well, how do we actually do that? Well, one thing is to figure out this polynomial here has alpha to the power of 7 as a root. What other roots could it have? And the approach that I'm taking here is a little bit long-winded, but it's the one that was in the lecture notes and slides and is pretty fail-safe. You don't have to think too much. So once you get used to all of this, then there are some shortcuts, one of which I'll show you. But first, let's do it the safe but boring and long-winded way. So a theorem in the note says that the roots of this polynomial here are, so roots are equal to, well, alpha to the power of 7. And then we've got alpha to the power of 7 times the number that we have here. That's in this case a 2, or if it were a different field over the ternary coefficients, then it would be times 3 and so forth. But here it's 2, so this is 14. And then I just keep doubling up, and that's all. So alpha to the power of 14 times 2 is 28. And again, doubling up, I'd have to triple up. For instance, if we're talking Z3 and multiplied by 5 if we're talking about Z5 and so forth. And here we've got alpha to the power of 28, but 15 of those alphas multiplied together give 1, so they just disappear, and this is the same as saying alpha to the power of 13. And then we've got alpha to the power of 26, and again 15 of those 26 alphas disappear, just turn into a 1 when multiplied together, and that gives us alpha to the power of 11. So let's have a look. This is going pretty well. There are quite a lot of roots, which makes my heart sink just a little bit, and you'll see soon why. But let's continue. Alpha to the power of 22, so that's 11 times 2, is equal to alpha to the power of 7, if we get rid of 15. And wait a second, now we've got a root that we had before. So we've got 1 root, 2 roots, 3 roots, 4 roots, and this is the same root as this one here. So we don't need to go on. We've found 1, 2, 3, 4 roots. Cool. So now by a theorem that we had in the notes, then the minimal polynomial is just the product of these expressions here. X minus each of these roots. So x minus alpha to the power of 7 times x minus alpha to the power of 14 times x minus alpha to the power of 13 times x minus alpha to the power of 11. And that's it. Ta-da! There's the minimal polynomial. But damn it, that's not the end of the story, unfortunately. Because yes, this is technically speaking the solution, but it's not in the way that we have to present it. We have to tidy up all of this, first make it a whole lot messier, and then tidy it up until we get a binary polynomial. And that's then the answer. So we've got a bit of work to do. Okay, let's get to it then. So I'll just get rid of this. And okay, now if we expand these terms, there'll be like 16 terms. We've got 2 choices for each of those brackets. We can collect those 16 terms just a little bit by saying, well, look, first of all, we've got x times x times x times x, x to the power of 4. And then we have, let's say if we have 3 x's and 1 not x, so that would be, well, we've got plus x times plus x times plus x times minus something. So we would have plus 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 and a minus multiplied together, so that would give us a minus. And so we've got a whole bunch of somethings here, times x, and I don't think I've made quite enough space for all of those somethings, so I'll just move it over there. And the somethings here will be these coefficients, alpha to the power of 7 plus alpha to the power of 14. By the way, if this is confusing you, this is just one neat, relatively neat and tidy way of writing up this expansion here. And I like to do it, I'm sort of used to it and can turn my brain off while I'm doing it. And the risk of errors is rather small when you're sort of used to it. But if you're not used to it, then all I'm doing is just expanding these brackets to get 16 terms, which is rather messy. And you might make mistakes, but when you tidy them up, they'll look like what I'm writing down here. Okay, so the first term, and then the second coefficients, and then, well, the next, I suppose, is something like this, where we've got x squared, and I'm writing it all over there and hoping that it'll fit. So we're choosing 2 of the x's, for instance, this x and this x, from this bracket and this bracket. Then we have to, then we're going to choose the non-x's, the minus alpha to something times the minus alpha to whatever is there. And we're going to do that in all the different ways that we can. So choose 2 of these any two of these four brackets. So 4 choose 2 is 6 ways of doing that. Take the x's from them and then take the alpha coefficients from the other two. And that's how we get all of these 6 terms that we're going to get here. So, and we've got minus, minus gives plus, so there's a plus there. And let's go. So alpha to the power of 7 times alpha to the power of 14, that was the first two, plus alpha to the power of 7 times alpha to the power of 13, plus alpha to the power of 7 times alpha to the power of 11. Oh, I made it a bit tight here. Plus, that was all the alpha to the power of 7s, alpha to the power of 14, alpha to the power of 13, plus alpha to the power of 14, alpha to the power of 11. And yes, I made it a little bit too squishy. Here we go. 2, and then 14, 14. Oh, I've got all the 14s, great. And now there's just the alpha to the power of 13, alpha to the power of 11, and I am done. Hopefully 1, 2, 3, 4, 5, 6, and each of these terms should appear 3 times, like the 7s. There should be 3 7s and so forth. So you can sort of check whether you got the right solutions a little bit at least. Okay, now for 1x, and this should have been a x squared, and this should have been an x cubed. What am I doing? Sorry about that. Yes. And now, if we just want 1x and 3 of the other terms, then we get, for instance, alpha to the power of 7, alpha to the power of 14, and 13, and alpha to the power of 7, 14, and 11, and then alpha to the power of 7, 13, and 11, and finally alpha to the power of 14, 13, and 11. And the way that I can say that quickly is just that, well, in the first term, here I'm choosing all of the alpha powers except the last one, except the second last one, except for the second one, and except for the first one. So there's a bit of structure and symmetry and order in this, so you can use that to write these things down a little bit quicker than otherwise. Okay, and finally we have one remaining term, which I might write somewhere down here. I'm sort of running out of space. I'll write maybe here. This is a bit naughty of me, but anyway. Plus alpha to the power of 7, 14, alpha to the power of 13, alpha to the power of 11, and there we go. Okay, so that was just expanding everything, and then, yeah. So now let's have a look at what we get when we try to tidy all this up. Well, first of all, x to the power of 4 is just x to the power of 4. And then we've got minus all of this stuff. By the way, at this point, we can, of course, just ignore the pluses and minuses. We're dealing with binary coefficients, so that really doesn't matter. But if you were to try to find a minimal polynomial where the coefficients were maybe ternary or over Z5 or whatever, then we wouldn't be allowed to do that. But here we can just say, okay, minus, plus, minus, who cares? They're alternating, that's all nice. Plus, minus, plus, minus, plus, so forth, yep. But we don't really care, so let's just say plus. Okay, alpha to the power of 7, 14, 13, and 11. Okay, let's go to the table here. So here we've got 7, so 7, 11, 13, and 14. Now let's have a careful look at these. How many powers of 3 are there? For instance, we've got 1 there, and 1 there, and 1 there, and 1 there. Oh, we've got 4 powers of 3, so when we're going to add them together, that's 4 times alpha to the power of 3, but 4 is the same as 0 in the binary system. So we have no alpha to the power of 3's here. Okay, what else? So we've got alpha to the power of 2, alpha squared. There are none here in the first term, alpha to the power of 7. What about alpha to the power of 11? Yep, there's one. There's alpha squared. And alpha to the power of 3, yep, we have now 2 of them. And alpha to the power of 14, no, there are none there. So we have 0. Well, we've got 2 alpha squareds, but that's the same as 0 alpha squareds. 2 is the same as 0 in these binary coefficients. Okay, well, what about alphas? How many alphas do we have? We've got 1 alpha, 2 alphas, no alphas, and no alphas. So we've got 2 alphas, and again, that's the same as saying no alphas. So no alphas. How many 1s do we have? And by the way, you might be thinking, why did I have to look at the number of alphas, alpha cubed, squared, and alpha? Because what I'm trying to get here is going to be a polynomial that doesn't have any alphas in it. So I really didn't need to do that, but I sort of like to do it anyway, just for a bit of a way to check whether my result is right. If I did do these calculations and I ended up with some alphas here, then I knew that I'd made some mistake along the way, and then I'd have to somehow figure out where it was. So there are a little bit of there's a little bit of redundancy in my explanations here, but that's for the purpose of checking whether my result is actually correct. So far it seems to be. So there are no alphas so far. What about ones? The coefficient, we found out that the coefficient in front of x cubed, well, luckily it didn't have any alpha cube or squared or alpha terms, because we're not allowed to have them. This has to be a binary matrix. But what about this coefficient there? Is it 0 or 1? Well, let's have a look. Alpha to the power of 7, 14, 13, and 11. If we add them together, well, we've done most of the addition there, but we just have to look at their constant term and add them together to get that last little piece of information. Alpha to the power of 7, well, it's got a 1 there. Alpha to the power of 11 doesn't have a 1. Alpha to the power of 13 does have a 1, and alpha to the power of 14 does have a 1 as well. So we've got 3 1s that we get from taking those terms and multiplying together. In fact, the sum of all of those 3 terms is indeed just 1. Okay, so apparently we have a 1 in front of the x cubed, and there we go. And now we have to look at the rest of the terms, the square term, the linear term, and the constant term. Now, I'll mention one little thing that can make life just a little bit easier for us, not by much, but just a little bit, a checks and balance type of thing as well here, a detail. This minimal polynomial is minimal in the sense that we can't find a smaller polynomial of degree less, that is. That's how we measure big and small, that has this as a root. So in particular, we can't have that the very last term, the constant term, is 0, because then this polynomial would be divisible by x. We could just divide the whole polynomial to get a smaller polynomial, divide the whole polynomial by x to get a smaller polynomial, which would still have alpha to the power of 7 as a term. So we know that the constant term there can't be 0. We're dealing with binary coefficients, so this term here is 1. But let's just check that our calculations are correct. Alpha to the power of 7, 14, 13, and 11. So add those numbers together. 7, 13 is 20. 14 and 11 is 25. 20 and 25 is 45. 45 is 3 times 15. And alpha to the power of 15 was 1. So that's just equal to 1 to the power of 3, which is 1. Yay, cool. So all of this is just 1. Well, that's a relief. Okay, we've still got two terms left. So we've got this term and this term. So I'm just going to quickly, to save a bit of space here, say, well, this is the same as alpha to the power of 21. And I could also get rid of 15 from that 21 there. So this is just alpha to the power of 6. And the same thing I could do over there. Let's use another pen so I don't mess up this red pen too much. And if I multiply alpha to the power of 7 and alpha to the power of 13, I get alpha to the power of 20, which I can simplify to 5. And what about 7 and 11? Well, that's 18 minus 15 is 3. And 27 I get here, which is 12 when simplified. Here we've got 25, which simplified gives 10. And here we have 24, which simplified gives 9. Oh, okay, cool. So we've got 3, 5, 6, 9, 10, and 12. And that's a bit easier than those expressions. I might just quickly do it for these as well. We've got 7, 14, and 13, so that's 34. And that's the same as saying 4. Subtract 15 twice. And here we've got 25, 32. That's just alpha squared. And here we go. I might just I don't know whether this is making it more clear or just more messy, but I'll just get rid of those duplicate terms up there and these two of the triplicate terms here. Here we've got 7, 13, and 11, so that's 31. Oh, okay, that's just alpha. Cool. To the power of 1 if you want. Sorry. No, that's right. And then alpha to the power of 14, 13, 11. So that's 27, 38. Haha. So if I replace them by 8, then I am done with those simplifications. And now, of course, I have to figure out what these sums are, and it's a bit hard to see now. So I'll just tidy it up 1 second. So alpha to the power of 6 and 5, 6, 5, 3, 12, 10, 9. And I hope that I can get that right. So I should have written it down somewhere. Okay, so alpha to the power of 6, alpha to the power of 5, alpha to the power of 9, alpha to the power of 3, alpha to the power of 12, and alpha to the power of 10. I don't know whether I got them in the right order, but let's see. 1, 2, 3, 4, 5, 6. I definitely got the right number of them. Hopefully they're right actual powers. And then I've got alpha to the power of, there was a 2 there that I got rid of. 4, 2, 1, 8. Oh, okay. That's easy to remember. They're just the powers of 2. So the next power would be 8 times 2, which is 16. So that would be alpha to the power of 1 again. That's sort of interesting, and it actually is interesting because, well, there is some significance to that. Anyway, there we go. And this was the, no, it wasn't the coefficient for alpha cubed, it was the coefficient for x. And now I'm just going to tidy up a little bit more and say, okay, we've already calculated that that was equal to 1. Now, if you were here in person, I'd ask you, aren't you riveted? Isn't this exciting? Look, I can't claim that these calculations are particularly exciting, but at least it's pretty straightforward to do. And if you do use those little tricks and checks and balances, then it's also hard to get wrong. I will show you a shortcut afterwards, though. Okay, so now we've got to take all of that stuff and add together. Alpha to the power of 6, 5, 9, 3, 12, 10. So 3, 5, 6, 9, 10, and 12. Do I have 1, 2, 3, 1, 2, 3? Yep. And so the alpha powers, for instance, alpha cubed powers, for instance, we've got 1, 2, 3, so 4. Yep, great. So that's the way it should be. We should have none of them. So 0 times alpha them. What about squared? We don't have any there. In fact, we can just ignore this term for now because we've added everything that it's got in it. So what about alpha cubed? So there's 1 there, there's 1 there, that's 2, 3, and 4. Ah, again, no alpha cubes. Yay, this is good news. We don't want any. And what about alpha? There's 1, 2, 3, and 4. Yay! This is going well. We don't have any alpha terms, and we might as well ignore this and this term because now we're only interested in the linear terms, which I suppose we've only got down here, and we've got 1 plus 1. Oh, okay, 0. So we've got plus 0 times x squared, and we might as well just write nothing. So now we just need this sum here. So alpha plus alpha squared plus alpha to the power of 4 plus alpha to the power of 8. What's that equal to? Well, let's have a look. Alpha to the power of 2 and 4, they are there and there. And then we've got alpha to the power of 8, and we also had alpha. Great. So alpha to the power of 4, we have that alpha and that alpha cancel out. We've got alpha squared plus 1, and oh, well, that in fact is this term there. So we've got 0 as well. Okay, so if you add these terms together, you get 0. Great, and then we just have 0 times x plus 1, which is 1. And that makes me very happy for 2 reasons, because there are no alphas here. And this is, by the way, the solution. This is the minimal polynomial of alpha to the power of 7, or this expression here. But the reason that I'm pretty sure that it's correct, apart from actually knowing the answer, my memory is not that great, but it does look very familiar, is that, well, there are no alpha terms here, and the very last coefficient is non-zero, so those things check out. But also, more importantly, I know that from looking at at previous questions that this is an irreducible polynomial. And, well, the minimal polynomials have to be irreducible, otherwise we could reduce them to something smaller that has alpha to the power of 7 as a root. So I'm pretty convinced that this is correct. The chances of getting a polynomial, a binary polynomial with no alphas and no zero constant term, and it being irreducible, are pretty low if you mess something up there. So I'm pretty confident that this is the answer, and indeed it is. So I was talking about a shortcut, and let's have a look at that. So you can do all of this, these calculations, and you saw that it wasn't too difficult, but it's not that fun either, and it would be nice if there are better ways to do it. So let's have a look at what we can do. So let's have a look, and I'll just remember this result over here, x to the power of 4. Is this even on the screen? It's, no it's not, haha, by magic. So, this is the minimal polynomial of alpha to the power of 7, and at the beginning of looking at this part of the question, we found that this polynomial here has 4 roots. If you remember, it had alpha to the power of 7, alpha to the power of 14, alpha to the power of 28, which was the same as alpha to the power of 13, and also finally alpha to the power of 11. So 4 roots. So in other words, the degree of this polynomial is 4. So let's just write this polynomial up in some way. So so let's say that it looks somehow like this. So C4 x to the power of 4 plus C3 x to the power of 3 C2 x to the power of 2 C1x plus C0. Okay, cool. Now we can simplify things just a tiny little bit by saying the coefficient there, C0, the constant coefficient, can't be 0, otherwise this would be an irreducible polynomial and therefore not minimal. So this is non-zero. We're talking about binary coefficients, so the only non-zero coefficient that we have is 1. Also, we can look at that top coefficient there, the C4 coefficient, and say that's got to be 1 as well. And the reason for that is that, so 1 there if you want. So the reason for that is that, well, yeah, the degree is 4 here, so it's either a 0 or 1. But in general, if we're talking about a non-binary field, maybe a ternary field or something bigger, then there could be different non-zero coefficients there. And then the question becomes, well, if you take some minimal polynomial and scale it up by something non-zero, by a non-zero scalar, then you get another polynomial of the same size, of the same degree, that also has whatever we're talking about, in this case alpha to the power of 7, as a root. So now you have 2 different minimal polynomials, and we don't want that. So one way around that is just to say, no, we are going to look at the monic polynomial among all these polynomials. And it's not hard to show that all of the minimal polynomials that you might get in that way, they are just scalar multiples, non-zero scalar multiples of this monic polynomial. So monic, that's just to say that there's a 1 in front of that top term there. So now, why did I do that? Well, look here. By definition, alpha to the power of 0 was a root of its minimal polynomial. So 0 is equal to this polynomial evaluated in alpha to the power of 0. So 0 is equal to this, which is equal to what we get when we evaluate this expression here in terms of alpha to the power of 7. So alpha to the power of 7 to the power of 4 plus C3 times alpha to the power of 7 to the power of 3, and so forth and so on. So C2 times alpha to the power of 7 squared plus C1 alpha to the power of 7 plus 1. Okay, so now we're going to just expand and tidy up a little bit. So here, this is alpha to the power of 28, which again we can reduce mod 15, or just reduce 15 from 28 to get to 13. Okay, and then we've got C3 here, and alpha to the power of 7 to the power of 3 is alpha to the power of 21, which is the same as alpha to the power of 6. Then we have C2 alpha to the power of 14. Well, that's just alpha to the power of 14, and then we've got C1 times alpha to the power of 7 and 1. Okay, now what? Well, again, all of this stuff has to equal to 0. So somehow we've got to figure out what C1, 2, and 3 are, what solutions there might be there to get all of this to vanish, to turn into 0. So that's what we're going to do. First, we can use the table again. Don't you just love that table? So we've got alpha to the power of 13 is equal to alpha cubed plus alpha squared plus 1 plus C3 times alpha to the power of 6, which is alpha cubed plus alpha squared, plus C2, which is equal to alpha to the power of 14, which is alpha cubed plus 1. And we're almost done, because now it's just C1 times alpha to the power of 7, which is, I recognize that from above. It's alpha cubed plus alpha plus 1, and oh wow, I'm almost running out of room. There's just enough room to squeeze that little 1 down at the bottom there. Now I've written all this up. Cool. But why did I do that? Well, now I'm going to tidy it up a little bit. For one thing, I can just get rid of this 1 here and that 1 there that I just wrote there. Try not to ruin that table. Okay, so that's tidied up a little bit. Here we go. But I still do have these C terms. So let's write things a little bit differently. So we've got the cubed terms, alpha to the power of 3 times 1 plus C3, and yep, plus C2. Any others? Yeah, plus C1. Okay, cool. So all of this stuff here has to be 0 if we want the alpha cubed terms to somehow cancel out. Next, we've got the alpha squared terms, alpha squared times, well, I suppose 1 plus C3. And we've got plus, so this is alpha squared. That was apparently just it. Okay, cool. And then we've got the alpha terms. We've got an alpha there, plus C1. Okay, that's cool. And so this was the alpha cubed, squared, linear, and just the constant term, which we have no more of. I tidied that up already. So, well, that's cool, because all of this stuff here has to be equal to 0. And all of this stuff here has to be equal to 0, and all of that thing there has to be equal to 0. In other words, we know already here that C1 is 0. And in fact, so this is 0 there. We can get rid of that. Okay, so that term has to cancel, give 0 if C1 is 0. And then we're left with, okay, let's look at that term then. 1 plus C3 has to be equal to 0, which means that C1 has to be minus 1. Or in other words, 1. We're talking binary numbers, so that means that C3 is equal to 1. So C3 is equal to 1. And I'll just write up what we've got so far. We've got that C1 was equal to 0. C3 was, might write them up nicely. C2 is whatever it is. We haven't found that one yet, but C3 was equal to 1. And C2, well, here we've got 1 plus this C3, which was 1, so they cancel out, plus a 0 over there, and C2 in the middle there, it's got to equal to 0 if all of this is equal to 0, so C2 is 0, and we are done. There we go. And in fact, we are done, because now we can just write up that polynomial here. If I get rid of all this junk, there we go. Here we go. Then I've got the coefficients right over here, and they are hopefully correct. Let's have a look. We've got x to the power of 4 plus C3, which was 1, so we've got one of the cubic terms, so x to the power of 3. Then we've got C2, which is 0. Okay, we've got no quadratic terms. We've got C1, which is 0, so we've got nonlinear terms. And finally, we've got the 1 over there, so we have 1 and the same polynomial. I'm a bit relieved. There's not a lot of room for error, but it's a little bit more confusing than what we're doing there. Possibly, I don't know. But anyway, that's another way of calculating these things, and a nicer way of calculating these things. So, that was the solution to part C, solved in 2 different ways. Okay, we've got one more question to go. So we spent a lot of time on part C, so now we just need one more question, and it's find all minimal polynomials of the powers of alpha. What? We just found one of those minimal polynomials. Now we have to find all of them? That's crazy. That's a lot of work. Yeah, it might be, but do not despair. Let's go. So first of all, well, what's the minimal polynomial of, let's say, alpha? So the minimal polynomial just of alpha to the power of 1. Well, I suppose that's just equal to, well, it's an irreducible polynomial that has alpha as a root. For instance, like that one there. That was exactly where we started. So, okay. This is, I've claimed, an irreducible polynomial, and sort of by implicit definition, if you interpret what that sort of stuff is saying, as I was mentioning at the very beginning, well, alpha is a root of that polynomial, so there we go. So this is just what we had, m of x to begin with, which is x to the power of 4 plus x plus 1. Now, that polynomial there has degree 4, so it's got 3 other roots. Cool, let's find them. So we've got alpha to the power of 1. That was one of the roots. The next is going to be alpha to the power of 1 times whatever that number there is. In this problem here, 2. So that's alpha to the power of 2. Then alpha to the power of 4. We're doubling here, 8. Alpha to the power of 16. Wait, alpha to the power of 16 is the same as alpha to the power of 1, which we already have. So we don't need that anymore. So these are the 4 roots of this polynomial there. So we've found more of these minimal polynomials. We've found the minimal polynomial of these 3 powers of alpha as well. So m2 and m4 and m8, they are all equal to this polynomial. So we're making some headway here. So m8 of x. Okay, what else can we do? Well, we just found the minimal polynomial of m7. So let's do that quickly. m7 of x was equal to this polynomial there, x to the power of 4 plus x cubed plus 1. And again, this minimal polynomial there has degree 4. It had 4 roots. In fact, we found them. One of them was alpha to the power of 7, and the other 3 were alpha to the power of 14, 13, and 11. So the minimal polynomials for those numbers, for 14, 13, and 11, or if we want to say 11, 13, and 14, are exactly this one as well. So we've found very many, well, we've found about half of the minimal polynomials by now. And I should say, well, how many powers of alpha are there? Well, look over there. We've got alpha to the power of 1 all the way down to alpha to the power of 15. So we've got 15 minimal polynomials that we have to find, but we're finding them pretty quickly. Here we've already found 8 of them. So this polynomial there, and this polynomial there. I can find one more polynomial really, really quickly, and that's alpha to the power of 15. Or if you want, alpha to the power of 0. So if I also write this as alpha to the power of 0. And the minimal polynomial of just the number 1 is super simple. It's just equal to m0 being equal to x minus 1. That's a perfectly fine binary polynomial, and it has 1, or in other words, alpha to the power of 0 as a minimal, as a root, and it is minimal. It's irreducible. It's monic, and so forth. So, how many roots have we done now? We've found 4, 4, and 1. So we've looked at 9 of the 15 roots. So we've just got a little bit extra to go. Okay, so let's have a look at, for instance, I don't know, M5. And sorry, it's a little bit messily written up here, but M5 of x is equal to something. Let's figure out what that is. I'm going to steal this space for workout and say, well, the roots of this polynomial here are alpha to the power of 5, alpha to the power of 10, if I double up, alpha to the power of 20, but cool, alpha to the power of 20, that boils down to just alpha to the power of 5 if we remove 15. And then we're back to where we started, so there are actually only 2 roots here. So we could be clever or whatever, but we could also just say this is equal to x minus alpha to the power of 5 times x minus alpha to the power of 10, and just expand. That's x squared minus alpha to the power of 5 plus alpha to the power of 10 times x plus alpha to the power of 15, which is 1. I'll just write that up though. Plus alpha to the power of 5 times alpha to the power of 10, which is equal to x squared. And this term here was alpha to the power of 15, which is 1, so that's going well. That has to be 1. And alpha to the power of 5 plus alpha to the power of 10, well, let's have a look over here. We've got x squared plus alpha plus, alpha squared plus alpha. And here we've got the same, alpha squared plus alpha. So they cancel out, just leaving us with the final 1 that's in alpha 10. So we have that this stuff here is equal to 1. So minus 1 times x, or in other words, just x. Plus and minus don't matter as we're talking about binary numbers. So x squared plus x. And finally, we've got alpha to the power of 15, which I've mentioned before is 1. And there we go. And is that irreducible? Yes, it is. And it's quick and easy to check. In particular, it doesn't have any root. 0 is not a root. 1 is not a root. Okay. And since it's degree 2, if it did have a root, then it would have a... if it were reducible, then we'd have to be able to factor it into 2 linear little x minus something times x minus something else. In other words, we'd have a root. We don't have any roots, so that is our answer. And of course, this is also the answer for what the minimal polynomial of alpha to the power of 10 is. Cool. So we've just got one, well, I don't know how many things we've got left, but we've got, in this table here, we've taken care of alpha to the power of 1. Did we? I think that was somewhere. Alpha to the power of, yes, here it is, alpha to the power of 1. So alpha to the power of 1, alpha to the power of 2. We don't have alpha to the power of 3. So let's have a look at that. I'll just tick off the ones that we do have. Alpha to the power of 7 we had, and 8, and 10, and 11, and 13, and 14, and 0. So the ones that we are missing are these ones here, alpha to the power of 3, 6, 9, and 12. Okay, let's start with 3. So alpha to the power of, the minimal polynomial of alpha to the power of 3. Well, what roots does it have? It has alpha to the power of 3, alpha to the power of 6, alpha to the power of 12, alpha to the power of 24, or in other words, 9. If we, oh wow, okay, this is looking suspiciously like those numbers over there. And then alpha to the power of 18. Oh, wait a second, that's just equal to alpha to the power of 3 again. So we in fact have that this minimal polynomial here has all of these remaining powers of alpha as its root. So it's got a degree 4 polynomial and it's irreducible. Now, here's a little shortcut in case you don't want to see a whole lot of calculations again. What degree 4 polynomials do we know that are irreducible and binary? Well, there are 3 of them, and 2 of them are here. This one here, x to the power of 4 plus x plus 1, x to the power of 4 plus x cubed plus 1, and x to the power of 4 plus x cubed plus x squared plus x plus 1. Now, that might not be immediately obvious, and I'll show you why this is. Well, I'll half show you why it is. So there we go. So you can check by looking at all the degree 4 polynomials which are irreducible that these are exactly the ones that we're looking at. And just to try to convince you of that a little bit, I won't show you the full details, but one little thing to convince you could be, for instance, that, well, if we say x to the power of 4 over here, so we're looking at degree 4 polynomials, and we've got a non-zero coefficient right at the end, we've got to have 1 in this case here, and then we're asking, well, something, 0 or 1 times x to the power of 3 plus something times x to the power of 2 plus something times x. Well, those somethings there, those coefficients, these 3 coefficients, have to be such that if we evaluate this polynomial in 0 or 1, then this is not going to be equal to 0, because then this polynomial would have 0 or 1 as a root, and therefore it would be divisible by x minus that root. That's not to say that that proves that it would be irreducible if that's not the case, but it does say that we can rule out a couple of things here. In particular, if we had an even number of these terms being equal to 1, for instance, like this, and let's get rid of the last term. For instance, if we have these two terms occurring, then we'd have, if we evaluate in 1, this polynomial, then we'd have 1 to the power of 4 plus 1 to the power of 3, 1 to the power of 2 plus 1. In other words, 1 plus 1 plus 1 plus 1 is 4, is 0, and 1 would be a root of this polynomial, and it would no longer be irreducible. So we can't choose 2 of these middle terms. So and we can't choose none of them either, because then we just have this expression here, which is also reducible because 1 is a root. So we've got to choose an odd number of these terms. So in other words, it could either be x cubed, just one term, or x squared, except this one's a little bit tricky because in binary, this is the same as saying x cubed plus 1 squared. So if you expand that, you get x to the power of 4 plus 2x squared, but 2 is 0 mod 2, and then you have the plus 1 term there. So this polynomial here, where we've just got the single term in the middle, that's not actually irreducible, it's reducible. So we don't consider that. And the other option where we just have one of these 3 terms is this one here. And finally, there's also the irreducible polynomial here. I haven't shown you that this is actually irreducible. In fact, I haven't shown you that any of these are irreducible, but you can go check. Well, it doesn't have 0 or 1 as a root. Sure. Could it be factorized into 2 quadratic polynomials, binary polynomials? And you'd have to spend a little bit of effort on showing that, but we've already looked at things similar to that, and you can verify for yourself that that is indeed the case. So there are actually only 3 polynomials of degree 4 that are monic. Well, sorry, in this case they're all going to be monic, and are irreducible, and we've taken 2 of them already as our minimal polynomial, so the third one is this one there. So that's just, again, another nice little shortcut to save us a whole lot of calculation. Did it actually save us time with all my explanations? I think a little bit, but maybe not as much as if you're doing it by hand without me to talk in your ear. So anyway, this is also, of course, the minimal polynomial of alpha to the power of 6 and 9 and 12. And I think that will conclude our solution completely here. The minimal polynomials of these. Do we have them all? We've got 3, 6, 9, 12. Tick, 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 tick. Yay! Indeed, we do have all of the minimal polynomials here, and it's a little bit hard to see them, so I might just highlight them. There's this one there, and this one there, and where do we have this one here, and this little one there, and this one there, and yeah, I think that's about it. So we've got 1, 2, 3, 4, 5 different minimal polynomials, but of degrees 4 plus 4 plus 4 plus 2 plus 1 is 15, and they have all of the powers of alpha as a root in total. So is there anything else more to say? I can't really think of anything, except I hope you understood what I was trying to say and now can go forth and do these things yourself. See ya.